Allow me to share my screen. Okay. I hope you can see my slide on techniques of integration. This is already part 4. And this is rationalizing substitution. Now, we'll first go to method 1 of rationalizing substitution. And this is in the case of integrals involving the nth root. So you have here n, so meaning this could be square root if you don't see any number here. But it could be a cube root, a fourth root, a fifth root, depending on the number that you see here on this part of your radical sign. So for integrals involving the nth root of the expression ax plus b, our main goal is that we eliminate this nth root expression. So in the process of eliminating the nth root expression, we assign a new numeral or a new variable to this expression that we have, the nth root of ax plus b. You cannot see the presentation. Can you see the presentation?
No, miss.
No, miss.
Oh my. Wait, class ha, I'll share again. Stop share. I'll share again. Okay. Can you see the presentation?
Yes, miss.
Okay. Sige. Now we are on method 1 of rationalizing substitution. Substitution in the sense that we're going to eliminate the radical signs that we're going to see in our original integral. Now, in the case of method 1, your integral has this expression, the nth root of ax plus b. So this n here could be any positive whole number, okay, because it's the nth root already. Now we want to determine, or rather we want to determine the integral, but before we can do that, we need to eliminate this nth root expression. One way to do that is to assign a new variable, any letter that you want, to this expression that has the nth root, or the nth root of ax plus b. So in this case, we assign it a u. Then for us to be able to eliminate the nth root expression here, we need to raise the whole equation to the nth power. That way, we take away the 1 over n in here for your ax plus b. So in the process, now on the left side, you will have u raised to n. And on the right side, you have now ax plus b. So you eliminate the nth root expression. So we do substitution, we assign a new variable, a new letter to that nth root expression, and the equation will be raised to the power, which is the reciprocal of the nth root. Okay, so in here it's 1 over n actually. This ax plus b is raised to 1 over n. So you're going to raise the entire equation to n. That way you eliminate the 1 over n power of the expression ax plus b. Okay, so to illustrate how it's done, so you have your example 1. So you have the integral of x over x, quantity x plus 1 raised to 2/3 dx. Now this expression of quantity x plus 1 raised to 2/3 is actually, if written class in the nth root expression, would be something like this. So this would be 3 here, and you have x plus 1 squared. Okay, so if this one is written in another form in which it's you're specifying the exponent, it would be this. So your problem is with this x plus 1 quantity raised to 2/3. So you assign a new variable to it, u equal to x plus 1 raised to 2/3. And the next thing that you do is you raise this entire substitution equation that you have to the reciprocal here of the exponent of the x plus 1. So it need to be raised to 3/2. So the purpose of that is for you to have the x plus 1 raised to 2/3 here converted to simply x plus 1. So in the process, you have now u raised to 3/2 equal to x plus 1. Then since you want the expression that will replace the x here in the numerator, so from this equation that we have, we get an expression of x in terms of u. So if it's x here that should be left, then this one should be transferred here on the left side. And interchanging the left side and the right side of this equation, so you have now x equal to 3/2 minus 1. Now remember that you are to substitute, because this is substitution, you are to substitute an expression in lieu of the original variable x. That way you will have you will not deal with the raised to 2/3 expression here. So if you're going to change the x into your new variable u, correspondingly you need also to change the dx. Now how do you do that? From the x that you have here, you do differentiation of the left side and the right side of the equation. So you will have here dx equal to, so you use power rule for this, that would be 3/2 u raised to 1/2 du. The derivative of this -1 is just 0 because it's a constant. Okay, so this is now your dx, this is your dx, and this is your x, and this is for the x plus 1 raised to 2/3. Now, the things that I have underlined here actually is going to replace your x here in the original integral. So your x is now u raised to 3/2 minus 1. The dx is this 3/2 u raised to 1/2 du. Now, if you wish to change the x plus 1 here raised to 2/3 directly to u, you can do that. Or you can change the x, actually, it would still be u actually if you do that. So you change the x here to u raised to 3/2 minus 1. So u raised to 3/2 minus 1 plus 1 raised to 2/3. And that would still be your u. Okay, wait now. So this is 3/2 raised to 2/3. So we get to multiply the power. So that would simply be u. Okay, why is it 1/2? So there's an error here, class. So that would simply be a u. Because in the first place, your x plus 1 raised to 2/3 is already the u. So this you don't have 1/2 here. Okay? Wait. It's after simplifying. I stand corrected. Now I see. This entire expression, class, actually is really u. Okay? Wait lang. This is really u. However, you have here u raised to 1/2, right? So this u raised to 1, you take out the u raised to 1/2 here, you still have u raised to 1/2 in the denominator left. The 3/2, the constant 3/2 that you have here will be placed before your integrand. So now you have u raised to 3/2 minus 1 over u raised to 1/2 du. After we did simplifying here, or simplification here. The best way to simplify your denominator, since it's already the expression x plus 1 raised to 2/3, it's already the u. So you need not actually substitute x here and then plus 1 because it would still be anyhow the u. So if you just simply write the u, that would still be correct. It would even be simpler. Okay? Now after you have done that, you have this u raised to 1/2. You're going to use it as a divisor to the two terms here that you have in the numerator. So u raised to 3/2 divided by u raised to 1/2 will require you to subtract the exponent. So 3/2 minus 1/2 is 1. Or that would be 2 over 2. So that is why you see here a u. And in here, your 1 over u raised to 1/2 will be u raised to negative 1/2. Now, the 3/2, of course, is just copied because it's a constant. Now, seeing your integral here, this will just be a simple integration using power rule. So, you just use power rule for this one. So, you have 3/2, then u raised to 2 over 2. And if you use power rule for this, again, you have 3/2, the constant in here, then power rule for this one. You add 1, and then the corresponding resulting exponent here is the denominator. So you have u raised to 1/2 over 1/2. Now this gives you an even more simpler expression, which is 3 over 4 u squared plus these two will go up. It will cancel with this 2 here. So you will have 3 u raised to 1/2 plus c. Now, before I go on, do you follow the process? From the substitution down to the use of the power rule here. Okay, so your answer now is in terms of u class, but your original integral is in terms of x. So what do? All the u's in here, all the u that you see in your answer should be returned back to its original x plus 1 raised to 2/3 expression. Okay, so that's what we're going to do in here. I'll just clear my markings, and in the next slide, you will see that being done. So you have this one, okay, and then you have to substitute x plus 1 raised to 2/3 to all the u's. So x plus 1 raised to 2/3, and it's squared, so this is squared. Then you have minus 3x plus 1 raised to 2/3 raised to 1/2 plus c. So if you're going to multiply, this would be now 3/4, okay, for the first term. Then this would result to 4 over 3 as the resulting exponent. For the second term, you will have 3. You have here 3, and then you have 2/3 times 1/2. The 2's cancel each other, leaving you 1/3 in the exponent. So you have 3 times x plus 1 raised to 1/3 plus c. Do you get it? Do you understand the first example? So the first example required you to eliminate. So I'd like to use the term eliminate the nth root expression by substituting or assigning a new variable, new letter to it. Now in the process, your integral is a lot less simpler to process or evaluate compared to the original. Okay, so remember the procedure in doing that. Eliminating the nth root would require that you raise your substitution equation to a power which is the reciprocal of the nth root. And the rest would just be your algebra coupled with your calculus. Okay, integral calculus, that is. Now, this is in the case when you just only have one rational, you only have one radical or nth root expression in your integral. What if you have several? Okay, in the second method, you have here an integral involving mixed radical. So one expression is the nth root, and the other expression is the mth root. Now, if you write the equivalent of this is right x raised to 1 over n. This one is x raised to 1 over n. Now, how do we eliminate these radical expressions in this mixed radical expression in your integral? You get the product of their roots or their exponents. So in that case, the resulting exponent of these two would actually be x raised to 1 over n times 1 over n. After that, then you assign a new variable to this new variable, which is now raised to an exponent, which is the product of the original exponents of your variable x. Now, I think it would be clearer if we have a specific example. Just go down. Now here in example 2, you have the square root of x divided by 1 plus the cube root of x dx. So you have here a square root and you have here a cube root. It's like you have here x raised to 1/2 and you have here x raised to 1/3. So true to what I have mentioned a while ago, you assign a new variable to these nth root expressions, but this time you need to multiply their exponents. So now you have here the 6th root of x assigned to a new variable u. Just like the first method, you will eliminate this one. How will you do that? You multiply, or rather you raise your substitution equation to the power which is reciprocal of this nth root. So it should be raised to 6. Now, after you're doing that, after you have done that, it would be now something like this. U raised to 6 is equal to x. Now, this expression that you have here, we'll erase. This expression that you have here is now this one. U raised to 6 equal to x. Again, just like method 1, you differentiate this equation. That way, you will have something to substitute to the dx in here in your original integral. So differentiating u raised to 6 will be 6u raised to 5 du, and x, of course, will be dx. Now, what will you substitute? You will substitute u expressions to this x square root, this cube root of x, and this dx. Now, how would you do that? So it's in here. Your square root of x is equal to this one. You need to replace it by u. But what is x? X is u raised to 6. So this x that you have here, you raise it to 6. So u raised to 6, and then you have it under the square root sign. You would want to replace the square root of x here by a u expression. So this is just like u raised to 6 divided by 2. This one is the same as u raised to 6 raised to 1/2. So you will have it as u raised to 3. Okay, rules of exponents. Now, you do the same with the cube root of x. So x will be your u raised to 6. This time it's cube root. So this one is comparable to u raised to 6. You raise it to 1/3. So that is why you see here a u squared. So in your original integral, you will replace square root of x by u cubed and cube root of x by u squared. What about the dx? The dx will be replaced by 6u raised to 5d. Now this 6, since it's a constant, you place before the integral. And then of course, you need to get the product of these two, adding the exponent. So that would be u raised to 8 divided by 1 plus u squared d. Now, since the degree of your numerator is higher than the degree of your denominator, you first resort to long division. Okay, before you even evaluate this integral, if the degree of the polynomial in the numerator is equal to or higher than the degree of the variable in the denominator or the polynomial in the denominator, first do long division. Okay, so we will do long division before we do the evaluation of the integral. So it's in here. Now, if you do long division, you will have this as the answer. How did you get that particular answer here by long division? So let me go to the Jamboard and show that to you. I'm sure the others know already, but just for review. I'm just opening Jamboard. Okay, I'll share Jamboard. So what you're going to, I hope you can see the Jamboard. Can you see the Jamboard? Class?
Yes.
Yes, ma'am.
So what you're going to divide is u raised to 8 by 1 plus u squared. Let me check. Okay, that's what we're going to divide. So we'll have here, you divide this one by this, so that would be u raised to 6. You multiply u raised to 8 plus u raised to 6. You subtract, you have here negative u raised to 6. And divide this, you will have negative u raised to 4. Then multiply this with this, so you have negative u raised to 6 minus u raised to 4. Subtract again, you will have u raised to 4. This divided by this would be u squared. Multiply, you will have u raised to 4 plus u squared. Subtract. So you have negative u squared. So this is negative 1. Then multiply, you have negative u squared minus 1. So the one that you have here is the remainder. So when you write your answer later, it should be u raised to 6 minus u raised to 4 plus u squared minus 1 plus 1 over 1 plus u squared. When you process the integral equivalent of u raised to 8 divided by the quantity 1 plus u squared. Okay? So if we go back to our slides, that's the thing that you see here. U raised to 6 minus u raised to 4 plus u squared minus 1, and this remainder. Now you can see that this is so easy to process because this will just require power rule. Though the 6, of course, the constant 6 will be written here just the same as it's written here in the previous slide. We already have a 6 here because of this derivative dx, which is 6u raised to 5 dE. Okay? So now we have this one. So if you use power rule, that would be u raised to 7 over 7 minus u raised to 5 over 5 plus u cubed over 3 minus u, the integral of this negative 1 du is just u. Now this one, we're just done with this. Last meeting, you have a du over 1 plus u squared, and that's actually the arctan of u. It's an integral yielding the inverse trigonometric function arctangent. Okay, so you have arctan of u. Now, since your original integral is not in terms of u, you have to substitute what u is. So what is u? So if we go back to our original integral, our u is x raised to 1/6. Okay, the 6th root of x. So that's what we did here. Your u was represented by x raised to 1/6. However, since it's raised to 7, you multiply the exponent by 7. So it's now 7 over 6. In here, it's 5 over 6. This one, you will have 1/6 times 3. 1/6 times 3 is 1/2. And this u is x raised to 1/6. Arctan of what is u? That's the 6th root of x, or x raised to 1/6. This should be multiplied by 6. And then you have the arbitrary constant of integration here, which is c. Now, do you have any question to these two rationalizing substitution? The next part of the substitution will be trigonometric substitution. Any question? Okay, so there's none. So let's go to trigonometric substitution. Okay? Now we go to the next slide. When do we use trigonometric substitution? The use of this technique, class, is only limited to these scenarios that you have here. Okay? So if your integral does not contain these expressions here, you cannot use trigonometric substitution. Okay? If your integral contains an a squared minus u squared, then you can let u equal to a sine theta. So the u variable in here, u is your variable, a here is any real number. Your u variable here was assigned an expression in terms of the sine of theta. That is why it's called trigonometric substitution. You need to know the square root of this real number in here. That way you can place it here together with the sine theta. That's in the case in which you have a squared minus u squared. If you interchange the manner of subtraction here, it's u squared minus a squared, then it would be the second of theta that you will be using in lieu of the sine theta here in the original substitution equation. Now, if it's plus, then it is u equal to a tangent theta. Again, I will repeat, this will only be applicable to expressions which has this particular form. You have a constant, a real number, minus the square of a variable or a function. In here, you interchange the two, the manner of subtraction, and in here you have addition. Okay? Now, how do we go about using trigonometric substitution? Just give me a few minutes, guys, huh? Okay, now you see here the square root of 4 minus x squared. This expression is comparable to a squared minus u squared. And based on our substitution equation presented in the previous slide, your substitution here would be u equal to a sine theta. U is equal to a sine theta. So in this case, you have here the a is 4. So meaning the a squared rather is 4. So the a is just 2. So your u, which is in this case is the x, is equal to a sine theta. A being equal to 2. Okay? Now since we're not using the u here and we have the x, then instead of using the u, you have here the x. I'm just placing here u so that you will recall the expression in which we are allowed to use the substitution equation u equal to a sine theta. Actually, we don't have u. It's x. Okay? Then differentiate this substitution equation. So you have dx equal to 2 cosine theta d theta. Now, what will you do? Of course, in your original integral, you change dx to 2 cosine theta d theta, and you change x here to 2 sine theta. So that's what is being done here. Your 4 minus 4, x is sine theta squared, and dx is 2 cosine theta d theta. Now, the 4 here, being a common factor, can be factored out, and we take the square root of that, and that is 2. That is why you see a 2 here, because you factored out the square root of 4 from these two terms here, which is 2. What is left is 1 minus sine squared theta from here, and we still have the 2 cosine theta d theta here. The 1 minus sine squared theta is equivalent to the identity cosine squared theta from your trigonometry. If you're going to get the square root of this, that would be cosine of theta. So this cosine of theta and this cosine of theta multiplied would give you cosine squared theta d theta. These 2 and these 2 will give you a 4. Now, this is under trigonometric substitution. A cosine raised to an even number or a sine raised to an even number requires that you express this cosine or sine in its double angle cosine equivalent. Okay, so you have 4 here. We copy the 4 and we replace cosine squared theta by 1 plus cosine 2 theta over 2 d theta. In the process here, class, if you notice, it's so easy now to do the integral. Because in here, you have 1/2 times 4. That would be the 2. And you have d theta. Okay? For this one, you have 4 still over 2. And that's 2. Then you have cosine 2 theta d theta. If you will integrate, this is just equivalent to 2 theta. You simply drop the d for the first term. This one will require that you multiply here by 2 and you divide by 2 outside. So that is now the reason why you only get to see a sine 2 theta plus c. Now, if you will represent the sine 2 theta by its equivalent identity, that would be the 2 sine theta cosine theta, okay, from your trigonometry. And you still have the 2 theta in here plus c. Actually, if you look at it, we have already determined or evaluated the equivalent integral of the square root of 4 minus x squared dx. However, this integral is in terms of x. Well, you have here thetas and the sine and cosine of that theta. So what will you do? Since you did trigonometric substitution in here, class, and that substitution equation is x equal to 2 sine theta, you need to construct a triangle wherein x over 2 is equal to the sine of theta. What is sine? Isn't it opposite over the adjacent side? Opposite over the hypotenuse. So then that's the corresponding triangle that we're going to draw. So I will I'll show to you the process in the next slide. Okay, so the continuation. Now I wrote a while ago that your sine theta is equal to x over 2. So if this is your theta, class, this is your angle theta, in the right triangle here, opposite x divided by the hypotenuse 2 is sine of this theta. So using Pythagorean theorem, you'll be able to get this particular adjacent side to theta. Square of this minus the square of this, and then take the square root of the difference. Okay? Now, you already have this. Now, what is this 2 theta in here that you have? Isn't it that theta is arc sine? Arc sine of x over 2. So you get the theta. It's here. Theta is the arc sine of x over 2. So meaning for this first term in here, the theta will be replaced by arc sine of x over 2 based on this substitution equation. As for this part here, you will have 2 times, what is the sine of theta? That's x over 2. And what is the cosine of theta? That would be the square root of 4 minus x squared over 2. So you could see here the answer. This is for 2 theta. This is for 2 sine theta, cosine theta, plus c. Again, we don't have much to simplify here, but in here we have the cancellation of the 2. So you have this x and this 2 here. So that's 1/2 x square root of 4 minus x squared plus c. So the answer of this integral is this, using trigonometric substitution. It's a little bit long. I'm referring to the process because after you did the substitution, it's unlike the rationalizing substitution, wherein you're simply going to resubstitute what the variable that you use is equivalent to in terms of the original variable. In here, you have to set up the triangle. But nonetheless, you still have to process, or you still just need to substitute what the sine is, the cosine is of a particular angle. It could be even tangent or cotangent depending on what your answer is. So in this case, this is the final answer to this integral. We cannot have this one as an integral yielding an inverse trigonometric function. It's because it's not in rational form. What I mean is, hindi siya fraction. Nakaamo gini siya, square root siya. So, hindi siya mag-yield either inverse trigonometric function or inverse hyperbolic function in terms of form and formula. So, no other way but to do trigonometric substitution. Now, before I go to the next example, do you have any question? Okay. Then I'll go to the next, okay? Go to the next class. We'll have next example. Still on trigonometric substitution. You have this. 1 over the quantity 1 plus 36x squared raised to 3 halves dx. Now, we cannot use the usual rationalizing substitution because of this here, the 36x squared. In rationalizing substitution class, the degree of the function that is raised to the nth root is only 1, meaning the variable has only an exponent equal to 1. In this case, we can't use it in here because it's now 2, or it's 36x squared. In terms of form, this is comparable to a squared plus u squared, which is actually the tangent. Okay? Your a here is 1 because a squared is 1, so a is 1. And your u here, you're just u, so your u squared is 36x squared. So it follows that your u is 6x. And this u, this 6x, will be equated to a tangent theta based on our substitution. However, our a is already 1. From in here, it's already 1. That is why you get to see only 6x is equal to tangent of theta because our a is 1. If it's not 1, then you can have another constant there. Now, the next step is you differentiate the 6x equal to, so I'll erase this a here, tangent of theta, left side and right side of that equation. So you have 6 dx equal to secant squared theta d theta. Once you have this, or if you want just the dx, then this could be divided by 6. So dx is equal to secant of theta squared d theta divided by 6. When you do your substitution, so that is why you see here 1/6 secant squared of theta d theta. Then you have 1 here plus 36x squared. What is 36x squared? So you have that as tangent squared theta. Why? You can see it here. If you square both sides, you will have 36x squared equal to tangent squared theta. So it's now changed here to tangent squared of theta. But if you want to really just substitute the x class, it's no problem because if x is equal to tangent of theta divided by 6, and if you're going to square it, this would still be the resulting expression, the tangent squared of theta. And since it's being raised here to 3 halves in the original, so you raise this also to 3 halves. Any questions so far before I continue? I just substituted the 6x equal to tangent theta expression and the dx equal to secant squared theta d theta over 6 to the original integral. No question? Okay, this one was simplified using the trigonometric identity secant squared theta. 1 plus tangent squared theta is secant squared theta. The 1/6 constant here was written before the integral. And you have here secant squared theta d theta. If you simplify the denominator, this is squared raised to 3/2. That would be secant cube. This would be secant cube theta. Then since you have secant squared here, this will cancel, leaving just with the secant in the denominator. Now, what is 1 over secant? That is the cosine of theta, d theta. If you integrate this, that would be the sine of theta. Of course, you will just affix the constant. Now, what is the sine of theta? Again, you construct a triangle which has, so what is your triangle now? Your tangent theta in your triangle is 6x over 1. Okay, this is understood to be 1. So this is opposite over the adjacent. Okay? Because this is not yet our final answer. We need to know what theta is so that our final answer will be in terms of x. Now, I will clear my markings and go to the next slide. So based on our tangent, I have here 6x over 1, opposite over the adjacent. If this is your theta, you can have your 6x over 1, and the hypotenuse by Pythagorean theorem will be 1 plus 36x squared. So what is the sine of theta? That would be 6x over the square root of 1 plus 36x squared. Since this is our answer, now we copy the 1/6 and we replace the sine of theta by this. 6x over 1 or square root of 1 plus 36x squared. We cancel the 6. Here, you have x over the square root of 1 plus 36x squared plus c. This is already the final answer for our integral. You have any questions before I go to the last example? Okay, so no question. Okay, my markings here will go to the last. Still on trigonometric substitution. So this one, of course, it's already implied. What will this be representing? So you have here in the denominator a u squared minus an a squared. So this is not a sine, but rather a secant. Your u is 2x. It's here already. And your a is 3, square root of 9. So our substitution equation is the u, which is 2x, equal to a, which is 3, secant of theta. Then the one that we're going to differentiate is this 2x equal to 3 secant theta. So you have 2 dx, 3, the derivative of secant theta is secant theta tangent theta d theta. So this one will be substituted back to dx, and our x will be 3 secant theta over 2 in here. Okay? Or this 4x squared is actually the square of this. So I'll show to you. Now, the x only, for the x only, it's 3/2 secant theta. However, it's being squared. So 3/2 squared is 9 over 4. Secant squared theta. Taken from here. And if this is squared, this will give you 4x squared. And this becomes 9 secant squared theta. So the 4x squared here is replaced by 4 secant squared theta in here. So your 4x squared is changed to 9 secant squared theta. taken from here. Then we copy the 9. Now this 9 and this 9, if you factor out, will have a perfect root of 3. So you have it here actually. But in this case, you already cancel this 3 in here and this 9 in here, leaving you a 3 in here. This 3 has secant theta, tangent theta, d theta is from the dx. So you transfer the 2 in here in the denominator. So we cancel the 3. So you will have now, let me check. So you have this 4 goes up. However, you have a 2 in here. So they will cancel each other, leaving you with a 2 here. So that would be 2/3. So that's the reason why you see here a 2/3. 3 over 2 in the denominator will be 2/3 when written on the numerator. So 2/3, you have secant theta, tangent theta, d theta. We copy the secant squared theta and the 9 here is factored out. Actually, this will give you a 3. That one. Okay. Secant squared theta minus 1 is tangent squared theta. Secant squared theta minus 1 is tangent squared theta. This one is a perfect root already. This would be then 3 tangent theta. So the tangent here will cancel with this. And you still have a 3 here. So that would be giving this a 9. And you still have a 2 here. And this secant will cancel with 1 here, leaving you with a secant here. And that 1 over secant is cosine theta. So 2 over 9 cosine theta d theta will give you an integral which is 2 over 9 sine theta. The same procedure as what we did in the first 2 examples, you construct a triangle representing this. So what's a secant? It's the reciprocal of the cosine. So it's hypotenuse over the adjacent. This is your theta. Then you determine this. So this would be 4x squared minus 9. So this is the opposite side. So let's see if that is the case. But before we go to the next slide, do you have any questions? The challenge with the use of trigonometric substitution is that you should be well aware or you have fully memorized the identities that were given to you in your high school. Actually, in your case now, there's no need to memorize because anyway, you can have your notes there while taking a quiz or exam, while answering a problem set. So you just glance on those notes that you have. That way, you can have the identities that you need within easy reach so that you can simplify your integral prior to evaluation. So this is our triangle. In my markings. And this is it. 2x over 3. Hypotenuse over the adjacent is your secant. And this is your opposite side of the angle. So for the sine, you have the square root of 4x squared minus 9 over 2x. So you will have a 2 over 9 and of course this sine. The 2's of course will cancel each other here, giving you a 1 over 9 square root of 4x squared minus 9 over x. Yes. Okay, so the 3 examples that were given you already covered the 3 different manner of substitution. One for the sine, one for the tangent, and one for the secant. So you use it whenever your integral cannot be processed using the formulas of inverse trigonometric functions or inverse hyperbolic functions. Actually, those formulas will not work if the degree of your variable here in the denominator is higher than 1. It should only be 1 or other than 1 specifically. If it's other than 1, then you have to really use trigonometric substitution. Do you have any questions? So you have here the application of the three trigonometric substitution equations. These are the three trigonometric substitution equations, and the two scenarios wherein you need to apply rationalizing substitution. For this, for the nth root, for an integral, determining the nth root of a function with with the degree of the variable equal to 1, or even not equal to 1, that would still be okay under the radical sign, because you can still have a process using rationalizing substitution, just like in the case here. Okay, x plus 1 raised to 2/3. The second one is when you have a mix of radicals of different roots. Any question? Okay, so if there aren't any questions, we'll have a break. Stop sharing. Okay, let me share my screen to you on method of partial fractions. Can you see the slide? Method of partial fractions. Can you see it, class?
Yes, Miss.
Okay, thank you. Now, the method of partial fractions, class, is applicable to rational expressions which you need to integrate, especially rational algebraic expression. So what I mean with rational is it's in the form of a fraction. You have a numerator and you have a denominator, and you may have a polynomial in the numerator. You also may have a polynomial in the denominator. Now we follow a 6-step process in determining the integral of such expressions. It's not complex compared to the other techniques of integration. It's only very long. So depending on the degree of the polynomial in your denominator. Now, the reason that this is called the method of partial fractions is you're going to represent the original fraction that is given in your integral to its equivalent partial fractions. It's like slicing an entire pizza or cake into smaller parts. That way, it is much easier for you to chew the pizza. It's the same thing with integrals. If you're just simply given a big a single complex rational expression, it would be very difficult, if not near impossible, for you to evaluate its integral. But if it is represented in the form of its equivalent partial fractions, the sum of its equivalent partial fractions, then it would be a lot easier to process or evaluate. Now, what is the 6-step procedure that we need to follow? That way you can determine the integral of a given expression. So let's look into these steps in partial fraction decomposition. So you are to set up your partial fraction decompositions with the unknowns ABC. We call these unknowns ABC, class, as the unknown coefficients, in which you will determine the value of. This ABC or D or F, depending on the number of partial fractions you have, are all written in the numerator. Okay, so it's all written in the numerator. You will see it later. The number 2, multiply both sides of the resulting equation by the least common denominator. Now, since you already represented your original fraction with the partial fraction equivalents with numerators ABC, what you're going to do is you multiply this entire expression by the least common denominator. In the process, class, you will be replacing the partial fraction equivalents, the sum of the partial fractions on the right side of the equation, by the factor that is not present in its denominator. The purpose of this step 2. Okay, you will understand it better when we go to the actual presentation of the solution. Then you need to simplify. You need to simplify the right side of your equation. Number 4 tells you on how you're going to determine now the value of the A, B, C, D, E that you have in the numerators of your partial fractions. You will equate coefficients of like powers of x and equate constant terms. This will also be shown to you later. Then solve the resulting linear system for ABC. And after that, the individual partial fractions will be the one that you're going to integrate, not the original fraction, which is complex and which is, of course, not factored. Now, this 6-step procedure will be presented to you in the examples later. So I cannot simply go to each of the procedures here without the example. So from time to time, I'm going to mention what step are we in the solution that will be presented to you. Now, take this study step. You will encounter, most of the time that makes it complex, you will encounter integrals in which the denominator is not factored. Even so, the numerator is not factored. So initially, before you dive on doing the 6-step process of determining the answer to your integral, which is rational in form, make sure first that you have already done the factoring. The factoring of the what? Both the numerator and the denominator. Now you may ask, why is there a need to factor the numerator and the denominator? You need to factor that way. If there are common factors, you can cancel them out and it simplifies the process for you. That is always the first step. Factor the numerator and the denominator. The second step is make sure that after factoring, and if you have already canceled out the common factors, you have checked the degree of the numerator and the denominator. The degree of the numerator should never be equal to or higher than the degree of the denominator before you even start this 6-step procedure. Meaning, if the degree of the numerator or the numerator is equal to or higher than that of the denominator after you have done factoring, and after you have done canceling the common factors, you need first to do long division. After that, okay ka na. Pwede ka na ka-apply sa 6-step procedure in determining the solution of your integral. So remember, the first, always factor the numerator and the denominator whenever possible. Okay? Para ma-simplify sila. Next is check the resulting rational expression if the degree of the numerator is already less than the degree of the denominator. If not, use first long division. Then after that, you can now process using the method of partial fractions. Now, to illustrate what I mean, I have here the next slide to explain that to you. If this is the original integral that you are to process, the numerator is of degree 3, the denominator is of degree 2. So before you even do anything, make sure that you do the long division. So if you do the long division, this is long division, this is your numerator, this is your denominator. So you have 2x here, and this is the corresponding answer. You have here 5x minus 3 as the remainder. How do we write the remainder? Now, the answer to this will be 2x. This is really the quotient plus the remainder, which is 5x minus 3. Then you have this as the denominator, x squared minus 2x minus 3. Now, it's the time for you to have this factored. Okay, you can factor now the denominator whenever possible. And since it's possible, it's like this already. Okay, so your original rational expression, just imagine that you have here the integral sign and the dx here, is now simplified into this form, 2x This one you can readily integrate. This and this, which you can as well integrate. The question is, the big question is, let me annotate. How did you get this one and this one from this expression? This one may be represented as A, and this one may be represented as B, or vice versa, because these two were written as the partial fraction equivalents of this original expression. Inilang niya. Ang 2x hindi na siya, kay answer na gina siya. So how we find the A and B, that will be explained on example number 1. But in the process of finding A and B, look here, you already did the factoring. You already factored x squared minus 2x minus 3 to this. And now, from this original fraction, you have these equivalent partial fractions. These two partial fractions, the sum of these two partial fractions is equal to this one. So there is the next problem for us to determine the solution of is how do we get this 3 and 2, which is initially represented by coefficients A and B. It was mentioned in the procedure that was read to you just a few minutes ago. Okay, so this will be the process of determining this one will be illustrated in example number 1. If it's already like class, if it's already known that this is already A and this is B, we can actually have this integrated. Ini ma-ln ma lang ni. Ini ma-ln man siya. Right? But the question is, how did you get the 3 and the 2? So we'll go now to type 1 under method of partial fractions. This is the partial fractions wherein your original fraction is, shall I say, represented as partial fractions in which the denominators are all linear. The denominators are all linear. Okay. Now, how do we go about determining this? So when the denominator of a rational expression contains a power of a linear factor, set up the partial fraction decomposition with constants A, B, C as your numerator. When the denominator of the rational expression contains already a power of prime quadratic factor, which is type 3, I will discuss later, set up the partial fraction decomposition wherein the linear numerators will be now ax plus b or cx plus d. This part I will discuss in type 3. I will only discuss this part in here in the first paragraph. So this is the example. This is your integral. This is the one that we have. Okay, so we will illustrate, or the example will illustrate how did you come up with this. So we go to this one now. In the previous techniques that were discussed to you, you will never find the answer to this. This can only be solved using the method of partial fractions, and as such, there's a need for you to know how it's done. So you copy the original fraction, but this time, you already had the denominator factored. The numerator, you did not factor because it's not possible to have it factored. So you just simply copy it. So it's now written like this. Now, the first step there that you are to do is you represent this original fraction into partial fractions in which the denominators are the factors of your original denominator. So you have x minus 3 here and x plus 1 here. The order is not really important. You can even have x plus 1 here and x minus 3 here. Even the coefficient representations, you can have a here, you can have b here, or you can have b here, you can have a here. Or you can have any letters that you want. It's just that for chronological processing of the undetermined coefficients, we just have it labeled as a, b, c, d, e. But you can have any letter that you want. So this one is, these factors that you have here are pure linear factors. As stated here, they are non-repeating because we have type 2 wherein these are being repeated. So what you're going to do now after this one is you go to step 2. You go to step 2, and that is you multiply this expression that you have with the least common denominator. This is your least common denominator. The purpose is you get rid of the denominator in this side, leaving you with 5x minus 3. And you get rid of this in here, and you get to multiply it with x plus 1. Why? If you're listening intently to my discussion a few minutes ago, it's this x plus 1 is not part of the factor that you have in here. So that's the thing that should be multiplied to a. The factor that is not part of the denominator of b is x minus 3. So it's the thing that should be multiplied to b here. That will be shown in the next slide. So what happens to the right side, it becomes 5x minus 3. And in here on the right side, you have a multiplied to x plus 1 and b multiplied to x plus 3. Why is that? Because we multiplied this by the least common denominator in factored form. Okay? Now, then you have to simplify. Third step, you need to simplify this one. So the simplification of this one is in here. Though class, when you go to your differential equations next sem, I don't really tell my students anymore to have this expanded. But in your case, you may do the expansion. That way, it would be easy for you to equate coefficients. But when you go to third year already, when you have the DE, I tell my students don't expand anymore, because that will just add up lines in your solution. You can go directly to equating coefficients. But since this is the starting point of the method of partial fractions, this is where we start introducing it. We're introducing it here in integral calculus. So we'll first do the expansion. So the second step is this, multiplication. The third step is simplifying. So this is the way you simplified it. So you have ax plus a plus bx minus 3b. Now, the fourth step, you already have simplified it. The fourth step is that you equate coefficients of the powers of x and the constants. What do we mean by that? Allow me to speak in Ilonggo para ka-intindi ka mo. Ang tanan nga may x sa left side, i-equate nyo sa tanan nga may x sa right side. Ang tanan nga constant sa left side, i-equate nyo man sa tanan nga constant sa right side. So, that's what it meant when we say you equate powers of x. Because if you have x squared here, class, for example, may x squared ka di, pangitao mo man ang may x squared diri sa kag amo na sila ang inyo nga i-equate. Kung may x cubed, then equate also the parts or the terms that has the x cubed. You also equate the constants. So in here, we only have the x and the constant. So we have 5x on the left, and we have ax plus bx on the right. You copy the signs of the term. So it's positive here, so we copy. Then you drop all the x's. You drop all the x's, or you drop all the x squared, so you drop all the x cubed. This is one equation. 5 is equal to a plus b. Now, when you equate constant, you have negative 3 here on the left. On the right, you have a. This is a constant, doesn't have any x. And you have here minus 3b. So you have the second equation. Why can't I write my 2? Negative 3 is equal to a minus 3b. Okay, you have already equated the coefficients of the powers of x and the constants. So that's our step, what is this? Step 4, 5 already. Next thing you do is determine the values of a and b, this one, no? A and b, by using algebra. You have two equations with two unknowns. You can use elimination or substitution. You can find the value of a and b. If you do that, the answer, I will not show it here anymore, but you can do that on your spare time. You will be able to get the answer, which is the one that is being shown here. I'll go back to that original slide. Where is that? This one. So your A must be 3 and your B must be 2. We go back. A must be 3 and B must be 2. 3, 2, 5. 3, 2, negative 3. Correct? So that's how the answer that you got there came about. You solve the two equations with two unknowns simultaneously, and you get the values of A and B. And once you have that, you can already process your integral. Where was that? This one. This one. So this, if this is your original integral, let's say I place here a dx, this is its equivalent already. You just have to answer that. So the answer for the first integral, I'll write here, that would be x squared. The answer for the second will be 3 ln of x minus 3, because this is u and the du of that is just dx. So this 3 you just place before the integral. This one is 2 ln of x plus 1 plus c. That's it. This is the answer to this given integral using the method of partial fractions. The process that was illustrated to you is the process of equating the coefficients of the powers of x and the constants. So I'll go back to that. And this is your answer. Wait, here, you have it here, and this is the answer already. So the process of dealing with these two equations with two unknowns is shown here, and this is your answer. The technique is the method of partial fractions. Now there's another technique, we call it the Heaviside method. That's an alternative, but it will only work easily, class. I'm not saying it will not work with other conditions, but it will work easily when your factors are linear. If your factors are already quadratic, it may be cumbersome as well, or mas malawig siya kag base magsala ka pa mag-multiply. What is the Heaviside method? So I'll show to you the Heaviside method. It's an alternative of the method that was shown to you in here. But do you have any questions so far with the first example? With the parts of the first example? Okay, so none. Sige. I will continue. The shortcut method is what we call as the Heaviside method, of course taken from the name of the engineer who is responsible for this simplifying method, the Oliver Heaviside. You have already this one. So this is already your simplified equation after you have multiplied this one by the least common denominator. Okay, this is already it. What we do with Heaviside method, class, is we think of a number that we add, or rather we think of a number that we substitute to this x here to make this term 0. That number is negative 1, right? Negative 1 plus 1 will make this term 0. So we assign x equal to negative 1. So correspondingly, you place here 5 times negative 1 is negative 5 minus 3, that's negative 8. Of course, this will be 0. Negative 1 minus 3 is negative 4. So from here, you can solve right away b, which is equal to 2. Because now you have negative 8 equated to negative 4b. So b is 2. Next thing is you think of another number that you will substitute to x here. That way, hindi naman yung term magiging 0. This will be the term that you can make 0. That number is 3. So if you multiply by 3 here, 15 minus 3, that's 12. 3 plus 1, that's 4a. This one will be 0. So a is equal to 3. Again, this will only be okay if you're just dealing with linear factors. No x squared in here. No expanded quadratic factor. If you have an expanded quadratic factor, you will still be later on dealing with the method of elimination and substitution because you'll still be forming equations. The shortcut method, the heaviside method, shortcut is applicable and will make things easy for us if the factors of our original fraction in the denominator are all linear. If not, wala man gyapon kay ti ma-substitute kada so hindi man gyapon tayo ma-solve kay tungod nga may iban ka pa nga solvon nga value sa x. Okay? So you can have this as an option if you want to use that when you encounter this particular integral. And this will not be the first time that you will encounter this. You will encounter this in DE next semester, next school year. And if you're going to proceed with CHE, God willing, you will still encounter this in process control, okay, in modeling, mathematical modeling. So that's how important is the method of partial fractions. Okay, any questions? So you will still come up with the same answer. Now, if you don't have any questions here, we go to type 2. Any question type 2? Any questions to type 1? The process class will still be exactly the same, only that you will have a different manner of writing the partial fractions depending on the identity of the roots. So in the first example here, type 1, your roots are linear. Any questions? None? Okay, we go to type 2. They are linear, but they are being repeated. They are linear, but they are being repeated, referring to the roots of the factor denominator. What should we do? When a rational expression contains a power of a factor in the denominator, be sure to set up the partial fraction decomposition to allow for every natural number power of that factor less than or equal to the power. Example, you can see here in the example, the denominator is already factored. This one is an example of a repeated linear factor. How do you write, or how do you break down or decompose it to its partial fractions? So this is how you do it. You have a over x minus 5 plus b over x minus 5 quantity squared. Should this be a 3, you should have here a c over x minus 5 quantity cubed. You get it? That's how you write the equivalent partial fractions of a repeated linear factor. This is a repeated linear factor. The repeated linear factor could even be in this simplest form, simply x cubed or x to the 4th or x squared. What do? You assign also individual partial fractions in here, wherein you have one for x squared, and one for x cubed. So all in all, since your denominator here is 5th degree, this is 2nd degree, this is 3rd degree, so 5th degree, expect partial fractions that are also having 5, or expect 5 partial fractions as its equivalent. So if you have, in the case of our previous example, since it's only 2nd degree, so you have 2 partial fractions. This one is 5, so you should have 5 partial fractions. The greater the degree of the denominator, the longer is the process, because you will have to determine your 5 unknowns, 5 undetermined coefficients. You get it? So express each of your factors in increasing degree in presenting your partial fractions. So you start with 1, then 2. Then you have your 1, 2, 3. Okay? Although pwede man siya unahon ni Ana, you will have your x, then x squared, then x cubed, then x minus 5, then quantity x minus 5 squared. We call this the method, we call this as the repeated linear factors. Now, don't do this. Later, I'll show to you the common mistake of my students. So you have this one. So repeated linear factor already. You have A, you have B. If you multiply this entire equation by x plus 2 squared, A need to be multiplied by x plus 2. B need not be multiplied because its denominator is already the LCD. So no need to multiply B with that. So you have this. If you equate coefficients class, you have 6. This one is expansion, expanded only. So 6x plus 7, you have ax plus 2, a plus b. If you equate coefficients for x, you have 6 here and you have ax here. You take out the x, a is equal to 6. Okay? Duha lang man ni sila ang may x. If you equate constants, you have 7, you have 2a and b. But since you know already a is equal to 6, so you have here 7 is equal to 2 times 6, which is 12. That would be negative 5. This is already your answer for the equivalent partial fractions of this. In terms of integrating, if this is your original integral, I just place the dx here, then you just integrate this separately. Something like that. So what's the integral? This will be another ln. So 6 ln of x plus 2. Well, this one will use power rule. Your u here is x plus 2. Your n is equal to 2. Your du is dx. By the way, your n is negative 2. So when you use power rule for this 5 is just a constant. So you will have minus 5. Then this negative 1 plus 1 is negative 1. So you will have 1 over x plus 2. This is already raised to negative 1 over negative 1. So this becomes plus c. So this is the integral of this expression. You get it? You use power rule for this one. Your u is x plus 2, your n is negative 2, your du is dx. So it's in here already. So if you use power rule for this, that would be u raised to n plus 1 over n plus 1. So this would be negative 1. That is why I wrote it here in the denominator. Over negative 1, that makes the entire thing positive now. This is your answer after you did apply method of partial fractions to these repeated roots. Any question? Any question? None? Okay. The common mistake that I mentioned a while ago with my students is this. Enlarge this one. This is a common mistake. They saw it as a repeated root, but they don't increase the exponent here. This is correct. The a over x is correct. Plus b over x minus 3 is correct. But this one is wrong. This should be c over x minus 1 quantity squared. Why is the entire thing wrong? Because once this one is wrong, wrongly represented, incorrectly represented, the answers for a and b will be affected. So your entire answer will be incorrect. Even though you wrote already the form of the first two partial fractions as correct. So please be very careful when you represent repeated linear factors in your method of partial fractions. You have any questions? Any questions? Okay, we go to the prime quadratic factor. Prime quadratic factor meaning, class, your quadratic factor is not being repeated. We also have a case of a repeated quadratic factor. I will show it to you right after the break when I give you the break on this. But the common ones are these three: the linear, the repeated linear, and the prime quadratic factor. What do you mean by a prime quadratic factor? This is the thing that is being referred to in here where is that? In here. when the denominator of a rational expression contains a power of a prime quadratic factor, set up the partial fraction decomposition with linear numerators. So your numerator now will not be simply an A or B or C, but it will constitute two terms, AX plus B or CX plus D, depending on how many quadratic factors you have. Okay, it's being reiterated here in prime quadratic factors. So I'll go to this one. So actually, this is already a challenging example. You have this. Let's say this is your expression. And your denominator has this x squared plus 1. This is an irreducible quadratic factor, meaning you cannot have this simplified further. It's standalone quadratic. Well, this one can be repeated. So you have here, you could see that for this factor, you have represented it by these two partial fractions which are being repeated. You have c over x plus 1 and d over x minus 1 quantity squared. For this irreducible quadratic factor, this quadratic factor is copied and the numerator this time is constituting two terms, not just a. It's now having ax, so you have an x here plus b. It could be, class, that you write these two first. You will have a over x plus x minus 1 plus b over the quantity x minus 1 squared plus cx plus d over x squared plus 1. This one would be written here as your last partial fraction. That's okay. It need not be in this order. But in here, it's already a challenging example because you already have a combination of a quadratic factor and a repeated linear factor. Now, how are we going to process this? What I have written here is the expansion already of the equation after this one was multiplied to the LCD. I'd like to show to you the entire process using the Jamboard. So I will share to you again the Jamboard so you could see the entire procedure. Okay, let's go to next page. Okay, let me check. We have negative 2x plus 4 divided by x squared plus 1 x minus 1 squared. Let me check if I have it correctly copied. Okay. Now, so we will write the partial fraction. So we have this quadratic factor. So we'll have ax plus b for its numerator. The denominator will be that quadratic factor. And you'll have your c over x minus 1 plus d over x minus 1 quantity squared. Now, this entire expression should be multiplied by this LCD. So, x squared plus 1 over x minus, multiplied to the quantity x minus 1 squared. So, I just write it there below. We don't have much space here. Okay? Now, I also suggest then in my DE students when they already reach differential equations that they need not write this procedure because it makes things longer. You just mentally do it. That is, you multiply this entire equation by this, and then the next line would be already the simplified expression. So you have negative 2x plus 4. Make sure that this negative you consider as the negative of the entire expression because that one is written here. Okay? Now, your ax plus b, you multiply to the factor that is not present here in the denominator, and that factor is x minus 1 squared. This c does not have the x squared plus 1, and still lacks 1x minus 1 because it should be x minus 1 squared. Okay, so that is why this c should be multiplied to x squared plus 1 and another quantity x minus 1. Your d has to be multiplied to only this because it has already x minus 1 quantity squared on its denominator. So it's just simply x squared plus 1. You get it? Now, this is what I do. I will not anymore expand because it may lengthen the process. I will just equate coefficients to save us time. So I will equate coefficients of x cubed. How did you know, Miss Ali, that you will have x cubed? If this is expanded class, this will be x squared already. If it's multiplied to this, that will yield an x cubed with this one. But if you cannot follow what I'm doing here, I'm writing it in shortcut manner, then you can do expansion in your spare time and redo everything. But in our case, just for illustration purposes, I will just go directly to what we need to determine, the coefficients A, B, C, and D. I don't have an x cubed here, so then my left side would be 0. In here, I should have an A. How do you know that, Miss Ali? This is x squared. If I multiplied it with this x, that would be ax cubed. So meaning I will have A. Okay? Now, this one is x squared multiplied to this x will be a cx cubed. So I will have here a c. For the D, none because I only have x squared. Okay? Now, if we do x squared, still the left side does not have an x squared. It's still a 0. Now, here comes the tricky part. This one, if expanded, is x squared minus 2x plus 1. When will I yield an x squared here? If this negative 2x will be multiplied to ax here, that will be negative 2ax squared, right? So I'll write here negative 2a. I don't mind this one in here because anyway, that would simply be an x. I'm just interested with the x squared. For this one, if this is multiplied to negative 1, that would be negative x squared times c, or negative cx squared. So I subtract c. And I have another one here, the d. Notice I haven't solved anything yet. Then I'll go to the x. Now this time in the left side, for the x, I have already negative 2. Okay, you see that? Negative 2. In here, I will have 2x. This ax times 1, so that would be a for the x. And then this one, negative 2x times b, that would be negative 2b. They will both have an x. This one will have an x and this one will have an x. Okay? Now for this term here, this one is x times c, so that would be c. Here does not have any x. Now for the constants I represent them as x raised to 0, meaning there's no x variable there. X raised to 0 is 1. So in here on the left side, I have minus 4. In here, this is 1, right? And d, that would be my only constant. So d for this term. This 1 and this 1 is negative, so I'll have negative c. And this one, we have d. See how complex it is? So it's really a challenge to determine coefficients if this is your integral. Okay, a combination of factors already. So you have 4 equations with 4 unknowns. So you use your algebra on how you find the unknowns. Okay, so we'll see if we can have it processed. Okay, we'll have this as 1. We'll have this as 2. We'll have this as 3. We'll have this as 4. Now, any suggestion from your end? How will I solve A, B, C, and D. If you cannot follow through this class, I'm not really forcing you to follow my shortcut way of doing. You can have this expanded, but I tell you, it will make one very long line here. Okay, so that is why I don't want to write one very long line. I'd like to go direct to the things that I only need. Okay, now, what equations do I need to process? That way I can find my notes. My coefficients. Any suggestion? Gigi, what equation will I process? There's no wrong or right answer here as long as you know how to find the unknowns. Your algebra is done already. You have done it in high school. So how would you determine A, B, C, D here? Oh, nobody knows? You will encounter far more challenging things than this. This is just algebra. What equation will you process first? Okay, let me stop sharing. Are you still there? Can you give me a reaction if you're still there? So why not suggest to me what equations will we work our way through? Why are you silent? You can just simply type 4 and 3 miss, 2 and 3 miss. Why no reaction? Oh, what's your suggestion? Okay, if you don't have any suggestion and solve it, then good luck on your own later. When you're the one who's going to process this, because even just your algebra, you are hesitant to give me the procedure and how you do it. You can have 2 and 3 or 3 and 4. So you can have 2 and 3. We can have 2 and 3 rather. So we'll have this 2 and 3. Okay, so if it's 2 and 3, you have minus 2a minus c equal to d. Or rather, plus d. So that's equation 2. Your equation 3 is negative 2 equal to a minus 2b. And I'll just place the c here, plus c. So I can have them. If I'll add, I'll get rid of the c. So I'll have minus 2 is equal to negative a plus d minus 2b. Okay, that's your 2 and 3. Now this is equation 5. Okay, another thing is we can have 3 and 4. So 3 and 4, this is your equation 3. Negative 2 equal to a plus b minus 2b. Okay, that's our equation 3. Negative 2a minus 2b. Oh, sorry, plus c. This should be c. Okay, that's c. Then we can have number 4. Minus 4 is equal to b minus c. B minus c, I'll add, plus d. Okay, again add. So I'll cancel the c's. So I'll have minus 6 is equal to a plus b. This one minus b. Equation 6. Okay, I will subtract these two. I get rid of the d. So 5 and 6. Minus a plus d minus 2b. Then for 6, negative 6a plus b minus b. If you will add, you will get the d. If you will subtract, you'll get the d's. This will be positive 4 equal to, this is minus 2a. This becomes plus minus b. Okay? What is our equation 1? Oh, it's in terms of c. What we have is a in terms of b. If a here is expressed in terms of b, you will have b and c. Okay, so we can express b. So your b here, your transfer here will be negative 2a minus 4. This will be equation 7. Then that b will be substituted to, so that we'll have a and c in here in equation 3. So substitute, we'll place it here. But maybe there's another route. I was not able to see it. Substitute b to 3. This b will be substituted to equation 3. Negative 2 is equal to a. So negative 2 is equal to a minus 2. And your b will be this b here, 2a minus 4. Let me check if it's all positive. Minus. Minus 2a minus 4. And then that's for the b being replaced there in terms of a. And then we have the c. We'll have here plus c. Okay, so I'm copying equation 3 here, and I have substituted the b expression to it. The b expression that we got in here. Okay, that way I will have an a in terms of c. So I have minus 2 equal to a. That would be plus 4a. That would be plus 8 plus c. You transfer it here, that would be negative 10, and that would be 5a plus c. Now, I have an equation of a in terms of c, and that's my equation 1 here. So 0 is equal to a plus c. So if I will subtract, I get to cancel the c's. I will have 4a, and this is equal to negative 10. So I get to know that a is equal to 10 over 4 is 5 divided by 2. If we divide by 2, so divided by 2, that will be 5. Okay, 5 halves. Once you have this, you can already find the c because a plus c is equal to 0. From here, you can get that a is equal to negative c, or c is equal to negative a. So your c is negative 5 halves. Now, knowing a and c, you just find any of the equations that you have here. You can solve for d. You have here negative 2a minus c plus d negative 2a minus c plus d is equal to 0. You just substitute the 5 halves here for a and negative 5 halves for c. So negative 2, you have 5 halves and negative 5 halves for c. A is positive, c is negative, and you can solve for d. D is the only unknown here. If you multiply everything by 2, so we'll not deal with fractions. So you'll have negative 10 plus 5 plus 2d equal to 0. Negative 10 plus 5 plus 2d. So it's 2d equal to 5 because this one is negative 5. So d is also equal to 5 halves. So what remains is b. So where can we get b? We have it here. So b is equal to negative 2. A is 5 halves minus 4. So b is equal to, we cancel this. You'll have negative 5 minus 4. And b is negative 9. Okay, so I'll place it here, negative 9. Is it negative 9? Correct, it's negative 9. So A is 5 halves, and C is negative 5 halves, and B is negative 9. What then would be the resulting answer to your integral? This is your original integral, class. Negative 2x plus 4 and this over quantity x squared plus 1 times the quantity x minus 1 squared. So ano siya? Isulat mo malang ng A kag B dala. So we'll write down A and B, okay? So you have the integral of negative 2x plus 4 divided by x squared plus 1 all over x minus 1 quantity squared is equal to. Let me check if I have copied the 2x minus 4 correctly. Correct. Okay. So it's ax plus b. Ax plus b. Your first integral, class, your x is 5 halves. Your a rather is 5 halves x. Your b is 9. The denominator for these two is x squared plus 1 dx. Okay, where are you getting that, Miss Ali? Aring original ng partial fraction. You place here the value of the a and b that you have determined already. You place the x with the a, and the denominator is x squared plus 1. The next two partial fractions will have x minus 1 and x minus 1 quantity squared. So we know that c is negative 5 halves. So I'll place it here minus 5 halves integral of dx over x minus 1. Because this is our partial fraction with the c. The d is positive 5 halves. So I'll just place it in here. Your d is 5 halves, integral of dx, that this time the denominator is x minus 1 quantity squared. Okay? Now this can be split into 2. I split this into 2. Okay, this one. So you will know that I have split it into 2, so I'll use a different color. This will be 5 halves integral of x dx over x squared plus 1 for the first term. The second term will be minus 9 integral of dx over x squared plus 1. So all in all, if I will split this into 2, this will be the 2 partial fractions plus these 2, I will have 4 partial fractions. True, because the degree of my denominator is 4. Okay? So I will now process the integrals. I will now answer the integral. So for this one, you can have an ln for this because your u in this case is x squared plus 1. Your du is 2x dx. You only lack the 2 here. You place 1/2 before your integral. So for the first term, your answer will be 5 over 4 ln of x squared plus 1 for this one. Right? Now I'll go to this. This is an arctan, right? 1 plus u squared, an arctan. So minus 9 arctan of u. What is your u? That's your x. Now this is our third term. Another ln, so I'll have 5 halves ln of x minus 1. What about this? If your u here is x minus 1, your du is dx. Your n is equal to negative 2. If you use power rule, this would be negative 1 over negative 1. So I'll make this negative minus 5 halves times 1 over x minus 1, because this exponent here becomes negative 1 already after using power rule, plus c. This is the very lengthy process of the method of partial fraction applied to this integral here. The same lengthy process that you may not fully like now, will not like it now, but the same process that you will encounter again in DE, the same process that you will encounter again in process control come 5th year. So you have to know really method of partial fractions by heart. Any questions? Do you have any questions? The process which is lengthy is this one. I intentionally chose 4 equations with 4 unknowns because I know your calculators would only have up to 3 unknowns, I think. I don't know if your calculators now can have 4 unknowns that it can solve 4 equations with 4 unknowns. It can with 3 equations, 3 unknowns. Why would I do that? Because I want you to really make proper use of your algebra. Simple as it seems, but you cannot process any complex expressions, mathematical expressions, if your algebra, by the way, is not really stable. It's not, as I say, it's not mastered fully well. Okay? So, ang process nga malawig, ini kay ma-decide ka pa kung di. Maybe there's a shorter process, but I just have to pick an equation here that would help us find the 4 unknown coefficients. Okay? But this is how you write the partial fraction equivalence. Actually, this one has an extension. It could even be classed like this. It could even be like this. I'll make this 2. So this will need another one. So if this is 2, you will have a case of a repeated quadratic factor. So you have another fraction here. I'll just insert it here. You will have another fraction. So you have the C and the D here. So you will have EX plus F all over X squared plus 1 quantity squared. You apply the principle behind repeated linear roots, and you marry it or you merge it with the concept of how you write the numerator of a simple quadratic factor, wherein you have 2 terms in the numerator, ax plus b. So in this case, you will have now ex plus f if this is squared, because you already have the c and the d here. If you find this very long, because this one has already 4 equations for unknowns, how much more this one? You will have to deal with 6 equations with 6 unknowns. But the process behind, the principle behind is still very much the same as what we have done in here. Only dati malawi gid siya kay imo siya solvon ang imo nga anom ka equations to find the 6 coefficients. A, B, C, D, E, and F. Do you have any questions? This one has an example in Canvas, in the document that was shared to you in Canvas. It was not placed in here in the PowerPoint presentation because anyhow, it's just an extension of the type 2 and type 3. So you'll just have to marry the 2 procedures. But as to a detailed example on this, it's there shared with you in Canvas, and it has a specific example as well. May example siya. So my goal lang for you this afternoon is to show to you how you write down the partial fractions and how you determine the coefficients, because the rest of how you find the integrals of each of the partial fractions were already taught to you based on the techniques that were covered. You have any questions? Any reaction? This is integral calculus. Just clear my markings. Do you have any questions? My time here is 4:47. We're supposed to have our class will end by 5:30. I'll give you a breather, a 13-minute breather. Come back at 5 p.m. because I like to go to what you have in Canvas to show you the document that I was mentioning. I have a 13-minute break and come back at 5 p.m. So let me share that document to you. Okay. Okay. I hope you can see case 4 under method of partial fractions. I did not include it anymore in the PowerPoint presentation because it's just an extension, as I've said, or the merging of the two principles in case 2 and in case 3. So this is a case wherein your quadratic factor is being repeated. You can see this is quadratic. This is irreducible already. You cannot have it factored to make it even simpler. And it's being repeated. So the manner you write the equivalent partial fractions for this, just enlarge it so you can see properly. It's like this. You have the first partial fraction having your quadratic factor. The numerator this time already constitutes of ax plus b. So this is the case of type 3. Wherein your numerator will constitute of ax plus b. Now, since it is being repeated, you need to add another factor. So you have quantity x squared plus 1 squared, and the numerator is cx plus d because you already used a and b in here. Now, to eliminate the denominators, you're still going to multiply by this LCD, which of course will give you a left side, which is x squared minus 2x plus 1, and a right side, which will require that this ax plus b numerator from your first fraction needs to be multiplied by x squared plus 1 because it only has this. It still lacks one of this to make it x squared plus 1 whose quantity squared. Whereas the cx plus d does not have any multiplier anymore. Then you still do expansion. If you need to expand this one, so you have ax cubed plus bx squared plus ax here, and then you have b. Okay, the manner it is written in here is already grouped. That way, the terms that have x cubed, x squared, x, and the constants are already together. Okay, so in here you have ax cubed, bx squared. This b constant and this d are together, whereas this ax and this cx are together in here, factoring the x. So when you equate coefficients for x cubed, which has your a here, your a is already 0 because you don't have an x cubed here on the left side. You only have it here. So a is equal to 0 already. Then for for x squared, if you equate x squared, you have here 1, and you only have b here on the right side. So that's automatically 1 for the b. For the x, you equate negative 2 on the left to a plus c. And since a is already 0, so your c is negative 2. For the constant 1 here on the left, you have to equate it to the sum of b and d on the right. Since b is already 1, then d is equal to 0. So you have two coefficients that are 0. In this case, you have a. So this is out of the picture already, and this d. So what remains is the b and the c. So your b is 1. And its denominator is x squared plus 1. So you have it there. That should give you an arctan of x. And for the cx here, that's your c is negative 2. It's here, negative 2. And your denominator is already the repeated quadratic factor, x squared plus 1 quantity squared. You can use power rule for this because if your u is x squared plus 1, the du of that is 2x dx. So you already have the 2x here. Okay? So your power rule will give you x squared 1 over x squared plus 1 raised x squared plus 1 raised to negative 1, which should be written like this, over negative 1. And you have this negative in here, so that makes it positive. What makes this example not cumbersome as the last example I've shown you? Because we have a standalone factor that is being repeated. It's not in combination with the other types of factors like the linear or like the repeated linear. So it is simpler in this case. So I have chosen that particular example, the last one I gave you in the slide. That way you will not get used to what is simple, because life is always complicated. You may not like it, but it's like that. So you better prepare for the complicated without, of course, losing sight of the basic and the fundamentals. So the fundamentals and the basics are all taught to you, the principles. Now, as engineers to be in the future, it's how well you apply the fundamentals, the basic, to situations that are not anymore fundamental. So I'm just giving you a taste of what is not fundamental. It could even be actually more complicated than the one that I have given you. In your time now, you are exposed to the net like 24/7, or maybe you do just face the computer on your cell phones when you are asleep already. And available resources are infinite for you. even when you face your teachers online, you are at a great advantage over the rest because you have your notes with you, you have your resources with you, you can open everything during assessments. Okay, you have your notes beside you which you can readily uh, get and refer to if there's a need for you to refer to. So make the most of that. Let's not capitalize on the things that are negative with our current situation, but let's look into the positives on uh, the advantages of it over then the time when we have face to face. Although probably class will have face to face next school year already. And stop sharing if you don't have any questions. And I don't want you to be caught